Thank you and good evening. So I'm pleased to be here to talk to all of you tonight about the Kepler mission and where we stand in our quest for other Earths. So this is an overview of my talk. I'll be talking a little bit about the design of the Kepler mission and why we had to design it so that we could do this job of finding Earth-Sun analogs. I'll tell you about Kepler's greatest hits, our key science results, moving on to the impact that Kepler has had on the field of exoplanets. I'll talk a little bit about how we finish this mission and complete the job of determining the frequency of Earth-sized planets in the habitable zone of Sun-like stars. And I'll tell you a little bit about NASA's next mission to find extrasolar planets. That's the TESS mission, which is slated for launch in 2017. And Julius Caesar up here is here to remind me that I'm here not to bury Kepler, but to praise Kepler. So to set the stage, there's a cartoon called XKCD, and this was one of the cartoons. At the time this was published, it has all 786 known planets drawn to scale. And if you squint really hard, you can see a small gray rectangle that contains the solar system. And if you can't see it, I'll zoom it. So this wasn't too long ago, just June of 2012, so just a little over a year ago. And this is our picture of extrasolar planets. Most of them are much more massive and larger than Jupiter, the biggest giant in our own solar system. And that's because, for the most part, it's a lot easier to find planets that are more massive and planets that are larger. So what Kepler has brought to this field has been the capability to push down the sizes of the extrasolar planets to a little bit smaller than the size of Mercury, in fact, comparable to the size of our moon. So the questions that Kepler is poised to answer are whether terrestrial planets, rocky planets like Earth and Venus, are common or whether they're rare. We want to know what sizes these planets are. Furthermore, we want to know what the separation is in distance between the planet and the star, because we're very interested in that range of distances for which liquid water could pool on the surface of a rocky planet like the Earth, i.e., how often do we find them in the habitable zone of their star? Furthermore, we want to know what kinds of stars have what kinds of planets. Stars come in a wide range of sizes and temperatures, from about a quarter the size of our sun to about twice the size of our sun for the brightest and most massive hydrogen-burning stars. The bottom line, are we alone? Well, up till now, we've known very little with respect to the terms in the Drake equation. We've known something about the star formation rate, but Kepler's poised to answer the question regarding the frequency of Earth-sized planets in the habitable zone of their stars. So how does Kepler work? Well, as you know, we can't resolve the disks of most stars with any telescope, and we don't try to with Kepler. What we do is we look for instances when a planet crosses in front of its star from our point of view, and we measure and monitor the brightness of the star over time, looking for these transit events and measuring the dip in brightness that happens when the planet crosses the face of its star, much like the transit of Venus just a little over a year ago. Well, how hard is it to find good planets? Conveniently for astronomers, Jupiter, if you see on the left, there's a silhouette of a Jupiter-sized body there in front of our sun, is about 1/10 the size of the sun by radius. So when it crosses the face of the sun, it blocks 1% of the light. Earth and Venus are 10 times smaller still than Jupiter. So when an Earth or Venus crosses in front of our sun from a galactic neighbor of ours, they would see a percent of a percent drop in brightness. And this is really small, a part per 10,000 or about 100 parts per million. So this is one reason why we have to go to space in order to measure these very small changes in brightness that simply are not attainable on the ground. So the key technical challenges are the size of the signal that we're looking for, 100 part per million deep drop in brightness lasting for a couple of hours perhaps. And that drives you to a very high photometric precision of 20 or 30 parts per million over the time scales of interest for transits. They do last typically from an hour to up to half a day. A central transit of Earth across the sun lasts 13 hours. Mars would last about 16 hours. So you need to sample the brightness often enough. Excuse me. You have to sample the brightness of the star often enough to be able to resolve the time signature that you're looking for. For Kepler, we sample every half hour. transiting planets are rare, even if planets are very common. That's because the geometrical probability of alignment, so that you would actually see a transit, is the size of the star divided by the size of the orbit of the planet. So that means that our galactic neighbors only have a 0.5% chance of seeing the Earth transit the sun. So we have to observe thousands of stars. In the case that eta sub Earth is small, we want a strong null result. And we don't know when a transit is going to occur. So you want to stare at a field of view long enough so you can see several transit events. So that's why Kepler was designed to fly and make these observations for at least 3.5 years, but could have done so for about 10 years based on the hydrazine fuel that we have to manage our momentum. So we launched in March of 2009, and 1 month later in April, we collected our first light image. Now, the field of view for Kepler is large compared to most astronomical telescopes. For a comparison, Hubble's field of view is about the size of a grain of sand held at arm's length. But the Kepler field of view is about the size of the palm of your hand. In fact, you see we have 21 modules, 42 CCDs, and the gaps in between the modules are large enough to contain the full moon. They're 0.5 degree. So this is a very large field of view by most telescope standards. But it'll be small compared to some of the successive missions. So now I want to tell you about Kepler's greatest hits. And I'm hoping this is going to be a double album, and you'll hear about that later in the talk. First and foremost, the first unquestionably rocky planet was Kepler-10b. This is a planet that's about 40% larger than the Earth. It's in a 20-hour period. And if you look at the red line, that traces out the model fit to the transits. Now, this data has been detrended, and it's been folded, but it has not been binned. So you're seeing the actual resolution of the data. In fact, if you look at the raw data, you can easily see by eye individual transit events in the data. Now, this is a bright target for us. It's 10th magnitude. That's why we have such good precision on it, so that you can actually see individual transits without needing to fold and bin. But it's 150 parts per million, and it's quite impressive to see this. This planet is massive enough and close enough to its star that you can actually measure the reflex velocity imputed by the gravitational tugging that it acts upon its star. So Jeff Marcy at Keck made measurements and measured reflex velocity variations of plus or minus about 3 meters per second. So that gives us the mass of 4.6 Earth masses, and together with the size, 1.4 Earth radii, that gives you a bulk density of 9 grams per cubic centimeter. Now we can compare that to the Earth, which is about 5.5 grams per cubic centimeter, but this is a much more massive object, so that doesn't tell you that it's not of Earth-like composition, as we'll show later. But Kepler didn't just detect single planets around single stars. One of the biggest surprises was how many multiple extrasolar planet systems we found pretty soon into the mission. So the first of which was Kepler-9, which is a pair of Saturn-size planets in orbit. One has 19 days and the other is about double that. But Kepler-11 is a system of 6 planets. Now this is a very compact system, and it must be very flat because we see all 6 planets transit each time they orbit. If you took this system of planets, you can see that all 6 of them fit within the orbit of Venus, and the 5 innermost all fit within the orbit of Mercury. So it is very compact. If you took this system and shrunk it down so that the outermost orbit was 10 inches, like an old LP record that some of you might remember, then all of the planets would stay inside the vinyl as the record went round. And if you take the 5 innermost planets and shrink it down so that the outermost orbit of the 5th planet is the size of a compact disk, then all the planets would stay within the plastic of this compact disk. So the dispersion in the inclination angles of the orbits for these planets in this system are very small, a couple percent, and that's similar to the solar system. And we found about 400 of these systems. So that tells you that nature loves to make planetary systems that are flat. So basically our picture of how solar systems form, planetary systems form, from a collapsing cloud of dust into a protoplanetary disk is correct. Now, these multiple transiting planet systems allow us to look at more stuff. In fact, what you can do is we see the transits of all 6 bodies in this system on the left, but you can measure the timing of each transit and compare it to when you think it should transit if it were a strictly periodic clock. And the Swiss would not like living in this system because they aren't strictly periodic. On the right are the transit timing variations, the discrepancies between the time you think a transit is going to occur and the time it actually does. In fact, these planets, the 5 innermost ones, are tugging on each other gravitationally. They're exchanging energy. And so you can see that there's an anti-correlated structure from each planet to the next one out. Now, what these transit timing variations do is they allow us to, in the first place, establish the planetary nature of these objects. And that's normally very difficult to do. But moreover, they allow you the opportunity to actually measure the masses simply from how the light is changing in the absence of any other measurements. So you don't have to go and collect radial velocities for these kinds of systems. Now, if you have the size of the planet and you have the mass from the photometric measurements, then you can look at the density and think about what this might be made of. Now, for Kepler-10b, it shows up here on this curve of radius versus mass. It's very close to what you would expect for an Earth-like composition. It's more massive, so it's more concentrated, it's more dense. Corot 7b, which was detected a little bit earlier, but whose rocky nature was a little bit slower to materialize, is very similar. But we have Mars, Earth, and Venus, and Kepler-10b and Corot 7b all lying pretty close to this curve. But these graphs are getting more crowded now. And so, in fact, if you look here, you have Kepler-11e, which is the least dense planet in the Kepler-11 system. It's about 0.5 grams per cubic centimeter. So it's consistent with an envelope of 16% hydrogen and helium with a mix of rock and water underneath. In fact, the Kepler-11 planets are all over the place. Now, we don't know exactly what all of these are made of. There's a great deal of degeneracy in making a planet of a given bulk density once you start having the ability to add admixtures of ice and hydrogen and helium. What we really want to know is when can you guarantee that a planet is rocky, has a solid surface that you can stand on? And that's the big question. We think somewhere below about 1.75 Earth radii that it's almost virtually guaranteed to be rocky. But this is one of the coming events in extrasolar planet science. In the next years and decades, we'll be trying to figure that out, in part from the results from Kepler. So I do want to underscore the multiple transiting planet systems. This is what is known as the Kepler orrery. This is an animation created by Dan Fabricki, one of our science team members, illustrating some of the many multiple transiting planet systems that we've detected to date. And you can see the time is advancing in units of 1 day. So it's quite a zoo of planetary systems out there that we found. And I think in no small measure, this is one of the most exciting and surprising things out of the Kepler mission. But here's another very extreme oddity. If you look at the light curve on the bottom, you see that there's a lot of hair coming down from this light curve. And if you zoom in, you can see there's something that's transit-like happening every 16 hours. Now, this was a real puzzle. Saul Rappaport, who really went to town on trying to understand what this was all about, decided that this is probably a case of an evaporating planet where you're not seeing the planet transit, but you're seeing the comet-like tail as the particles that evaporate off the surface actually condense and form a plume. And this has gotten more substantial with the release of a new paper now that has established that the transit depth of the comet-like tail is correlated with the stellar variations over time. So it's tying the star to the object. So this is most likely a disintegrating planet that's smaller than Mercury, and it doesn't take it much time to actually evaporate. We just happen to be fortunate enough to be looking in the right place at the right time, which means there are probably a lot of objects like this out here. This is just the first example that we've found. Circumbinary planets. Well, everybody remembers Tatooine from Star Wars. I remember myself, I got involved in extrasolar planet research back when a few friends of mine were collaborating with international astronomers to look for planets around Cm Draconis, which at that time was the smallest known eclipsing binary. If you have planets forming in the same plane as the two stars form, you would expect for eclipsing binaries to be able to see the planet's transit. So we've been interested for about 20 years now in finding such planets, planets which orbit not just one star, but a pair of stars that are in a short period orbit. In fact, with Kepler, we've now found a half a dozen of these systems. There are probably another half dozen or so in the hopper, and they've all been found to date by looking through the data by eye. So I'm sure there are a lot more in the data that you would have to use a computer program to find, but nobody's put together a computer program to do that through the Kepler data in general. At any rate, what's very interesting is that with the fifth or sixth such system that we found, Kepler-47, we found the first planet in the habitable zone. Now, this didn't happen so quickly with single planets around single stars. It took a lot longer for us to find a habitable zone planet for single stars. So this may be telling us something very profound about circumbinary planets. If you look up in the sky, 3 out of every 2 stars you see is a multiple star system. So it may be that most of the habitable planets are in circumbinary systems. So Kepler-47c in the middle of the habitable zone is somewhat larger than Neptune, but that's not to say it might not have a habitable moon. It's an open question. At any rate, it's very exciting to see this happen so quickly. Now, more recently this year, we advanced the knowledge of finding Earth analogs with the Kepler-62 system. To date, this is the system that's most like the solar system you and I live in. It has 5 planets, 2 of which are in or near the habitable zone. Kepler-62e is at the inner edge of the habitable zone, and it's about 1.6 Earth radii. And it is close to the inner edge, so it may be more of a super Venus than a super Earth in terms of what it's like. Kepler-62f is a little bit smaller, 1.5 solar radii, 1.4 Earth radii, and it's smack dab in the middle of the habitable zone. So that's not to say these planets are really habitable. That determines a lot about what the atmosphere is like. But it certainly is pushing us down towards Earth-sized planets in the habitable zone of Sun-like stars. Now, Kepler-62 itself is a K-star, so it's somewhat cooler and smaller than the Sun, which means that the habitable zone, drawn to scale here compared to the solar system, is a little bit smaller. So a habitable zone orbit is slightly shorter than that of a habitable zone orbit in our own solar system. Kepler-69, which was announced at the very same time, has a super-Earth that's 1.7 Earth radii, so 70% bigger than Earth by radius, at the inner edge of its habitable zone. And what's exciting about this system is that this star, Kepler-69, is a very close cousin of our own Sun. They're both early G stars. So it's very exciting to see this happen. Now, this also underscores the importance of knowing your stars well, because when we first detected this in the pipeline, over a year before it was recognized how interesting it was, we thought that actually the star was much bigger than it actually is. And so we thought this was a much less interesting system, because if you have a much larger star, the habitable zone is pushed way out, and of course the planet's much bigger in your mind until you actually figure out what's going on. So one of the major tasks for Kepler is to have astronomers in the general community, and we have a working group called the Stellar Properties Working Group that's working to update the knowledge of the parameters of the stars that we're observing, because you only know your planets as well as you know your stars. So I can't tell the story without talking about asteroseismology, which is the study of the propagation of acoustic oscillations in stars. So stars are great big balls of fluid, and acoustic waves propagate through them. You have disturbances on the surface, which create acoustic waves which travel inwards, but then they get reflected back out. And then if they come back to the same point that they started, then it's coherent. So you can set up coherent oscillations. So what I have up here is a grid, 3x3 grid of power spectra for 9 different stars. And the stars get cooler as you go to the right or hotter as you go to the left. And they get more massive or more luminous as you go up. And if you look really hard, you can see that there's a comb of frequencies at which the star is oscillating acoustically. And this comb moves to the left, moves towards lower frequencies as the star gets bigger. Stars, just like bells, the frequency of the tone that is sounded when you ring the bell is dictated by the size of the bell. And it's the same with stars. So what these measurements allow you to do is to measure the size and the mass of the star and estimate its age really well. In fact, you can measure the mass and the size to a couple percent. And these are just point sources. You're not resolving them, but you can measure their sizes extremely accurately. And that means that we know the planet size extremely accurately. That's why we know that Kepler-10b is 1.4 Earth radii, is because of the asteroseismology. Without that, we wouldn't know that it was really 1.4 Earth radii. So this is really amazing. And what's great about Kepler is that it's allowed us to do this for over 500 solar-like stars. If you look at this little inset, that's the knowledge of the state of this field pre-Kepler, which was a couple dozen stars for which these P modes had been measured. But for Kepler, we're actually looking at hundreds of stars and spanning the entire HR diagram. It's really easy to do this for red giants because typical oscillation period is hours to days and longer. So we don't need to use this very precious commodity known as the short cadence targets, which we monitor every minute, for which we can only collect up to 512 stars. Moreover, we can look deep inside these red giants to see what's happening. It turns out that as red giants age, at first they're burning hydrogen in a shell surrounding the helium core. But then they go through a helium flash where you start fusing helium in the core. And when the core gets that dense, the gravity or buoyancy waves inside the core can make it out to the surface and perturb the shape of the star and alter the power spectrum, alter the frequencies. And so you can actually distinguish two red giants that look exactly the same from the outside. They're the same size, they're the same color, they're the same temperature. They look identical. They look like identical twins, but they're not. One of them is much younger and is burning hydrogen in a shell, and the other one is burning helium in the core. So this is really wild because we're using Kepler like an X-ray machine. And so you can derive quantities, the periodic spacing and the changing in the period of the gravity waves, and you can separate the hydrogen burning stars from the helium core burning stars very easily. Beyond this, you can actually measure the differential rotation between the helium core and the convective hydrogen envelope. And we've done that for some of the stars in our survey too, and that's really wild. So what's Kepler's impact on the science of exoplanets? I'm going to tell this story with pictures. And so here's Earth, an Earth-sized planet, Neptune-sized planet, Jupiter-sized planet, and this is how the field advanced from 1995 when the first planet around a main sequence star, like the Sun, was discovered, 51 Peg. The pink spots are those planets detected by radial velocity variations. So you see the bulk of the planets were discovered this way. Transiting planets started being discovered in the year 2000, and they were limited up till 2009 to planets that, for the most part, were as large or larger than Jupiter. Although there's a notable exception down here, that's Corot 7b, which was detected from space rather than from the ground. And you see that we've gotten better with radial velocity, so we're pushing down towards planets that are smaller than Neptune. And for most of these planets, we don't know exactly what the size is, so we're using a size-mass relationship because the radial velocity planets, you measure the mass. But this gives us an indication of where these planets lie relative to the Kepler sample. Now here's how the field advanced between 2009 and 2012, and you see that we're filling in more radial velocity planets down here. Maybe there are a few transiting planets as well. Most of them are up there. So here are the Kepler candidates and planets detected to the beginning of this year. In fact, it's saturated. So what you see is that at this point in time, we've analyzed 2 years of Kepler data. And you see this diagonal wall here where we're trying to push out to orbits that include the orbital period of the Earth, but we're able to, because of the fact that we see many more transits, push down to very small planets for very short orbital periods. And we've only fully exploited the first 2 years, so half of the data set. So we expect this diagonal wall to move to the right as we push down into the data and do a better job with the data processing. So as of today, according to exoplanets.org, which is a little bit more conservative than the Exoplanets Encyclopedia, there are 728 confirmed planets. 141 of these were detected by transit, but not by Kepler. 136 confirmed planets are Kepler transiting planets, and 426 were discovered by radial velocity variations. Kepler today has over 3,500 planetary candidates that have yet to be confirmed, but we believe that 80 to 90% of them are bona fide planets. It's turning out that it's a lot easier to find the planets in the Kepler data than it is to get enough telescope time to actually do the confirmations. It's a nice problem to have. So what do we make of all this data? Well, if you take the data and you bin it and count the number of detected candidates and planets in each of these size bins, then this is the histogram you get, with most of them Neptune size, 1290 Neptune size objects, 2 to 6 Earth radii. And then it falls off. But there's a lot of observational bias in this direct histogram because we're sensitive to the geometric probability of alignment I told you about before. We're also sensitive to the size, so it's a lot harder to find Earth-sized planets because of the noise. For Neptune-sized planets, for almost any star we look at with Kepler, we found all the Neptune-sized and larger planets you're going to find at orbital periods short enough so that you would have seen one or more of them over the course of the mission so far. But for the Earth-size and the twice Earth-size objects, we're not complete. Nevertheless, you can make an estimate of the completeness, and this is the histogram you get in terms of the intrinsic frequency or occurrence rate of planets as a function of their size. There's a dramatic rise from Neptune, large Neptune-sized objects, to Neptune and smaller-sized objects. And so that's definitely real. This is a dramatic increase. But then something interesting happens for things that are 2 to 4 Earth radii and smaller, and that is that it seems to flatten out or actually decrease. And so I think this is telling us a couple of things. One is it's most likely, several people have looked at this and they see the same thing. It's most likely the case that the formation process for terrestrial bodies is different from that for the ice giants and the gas giants. And this is telling us that. It's also true that we probably don't understand our instrument and we probably don't understand our data well enough to do a really good job down here. And so I think there's a little bit of wiggle room in terms of how this goes, whether it continues up a little bit or whether it's flat or whether it decays. But it's going to be close to this. It's not going to be radically different. Now, a different way of looking at the data is to say, what about the habitable zone? Well, you can convert, for each of these planet candidates, you can convert the distance and the size and effective temperature of the star to the effective flux you would see at the surface of this planet. And this is a log scale, so at 0, that's the same flux as is received at Earth. So you see Earth up here. Now, the 2 green lanes indicate 2 different ideas of what the habitable zone is. There's a lot of debate over what exactly makes a habitable zone. The dark green lane is a theoretical model. And then the light green lane is an empirical model that's been adopted by many people in the field that extends inwards to about a little bit outside of Venus's orbit to a little bit further than out beyond Mars. There's a great deal of uncertainty in what exactly the habitable zone is because it depends on the properties of the planet as well. Nevertheless, the dark green disks indicate the size of planets or candidates that have been found that are smaller than twice Earth size, so you can actually compare them directly with the Earth there. 2 years ago, we announced the discovery of the first superplanet found to be transiting in the habitable zone of another star, and that was Kepler-62b. So it's about 2.4 Earth radii. But since then, in the last 2 years, it's gotten a lot of friends. And some of these are around very small planets. So let me just point those out. Some of these are around very small stars. So when you're talking about stars that are 3,500 Kelvin, you're talking about M stars, the smallest main sequence stars. And so their habitable zones are very compact. We're talking maybe 20 days, 30 days for the habitable zone. And the fact is we have very few M stars in our survey. We only have 3,000 out of the 170,000 stars we might be observing at any given time. Only 3,000 of these stars are M stars. So the fact that we found so many habitable zone candidates and planets around these M stars indicates that M stars like to have planets in the habitable zone. Now, the statistics are somewhat in flux, but here's a reading of the literature as of a few months ago or so. And that is that people who are studying our data have come to the conclusion that 17% of main sequence stars have an Earth-sized planet within 85 days in period. Moreover, if you relax the condition on the size of the planet and the size of the orbit, at least 70% of stars have a planet with a period of less than 400 days. That tells you that if you look up into the night sky and you see a main sequence star, it has a planet. 45% of F, G, and K stars will have a planet with a radius between 1 and 3 Earth radii with periods out to 500 days. So this is a study that's being done by Jeff Marcy. With respect to M-type main sequence stars, 60% of M dwarfs harbor planets smaller than Neptune. Moreover, somewhere between 15 and 50% of M dwarfs harbor planets smaller than 2 Earth radius in the habitable zone. And this is really astonishing. This says that if you're interested in observing and characterizing an Earth-sized planet in the habitable zone of a nearby star, it's just around the corner. It's like, it might be 6 6 light years away. It's not really far. To find a transiting one, it might be a little farther, like 20 light years away. But this means that all of us who have dreamed about learning something about a habitable zone extrasolar planet that's similar in size to the Earth, it's within our grasp, I think. So in terms of defining eta sub Earth, the frequency of Earth-sized planets in the habitable zone of Sun-like stars, are we there yet? The answer is no. But I think we're as close as Dorothy and her friends were when they saw the Emerald City at this point in time. But we have to remember what they had to learn, that is, it's no time to fall asleep now. We still have to keep on pressing forward to learn what we need to learn, both from the Kepler data and about the stars, in order to complete this job. So earlier this year, in May, it was time for another birthday for Kepler. And I'm sure that Bill Barucki, our science PI, was thinking that we'd have a lot more candles to blow out as the years went by and observing with Kepler. He never dreamed small. Unfortunately, the reaction wheels got in the way of what we were doing. So we lost our second reaction wheel about a year after we lost the first one. And now we only have 2 reaction wheels, and we need 3 to point and collect science data to continue the Kepler mission as it stood. But I was with Bill the day that we learned about this, and I walked into his office and I said, Bill, you asked for a 4-year mission, and that's exactly what you got. And he laughed and said that, yes, that's right. And he was delighted by the fact that we got so many years out of it, and we've learned so much. There's still work to do. Natalie Battaglia is our mission scientist, and she's been thinking a lot about how we actually are going to come up with a good estimate for eta sub Earth. And so here are some of the ingredients that we need in this cake. We need to mine the data and get all the planetary candidates and all the planets we can out of it. We've got 4 years of really great data. We need to make the most out of it. We also need to understand the completeness of the planet discovery system. What fraction of planets that are in the data are we actually detecting? We're going to use a combination of theoretical studies, but also injecting artificial transits into the Kepler data. The flight data will help us understand our completeness. We also need to understand the reliability of the sample. What fraction of the candidates are imposters, are not really planets at all? We'll also address this in part with simulations where we inject artificial background eclipsing binaries, which can mimic transits, into the Kepler flight data and see how the pipeline does in detecting those signatures and correctly attributing them to being background eclipsing binaries. We need to know more about the stars. And this is a big problem, but fortunately we have a lot of people in the Stellar Properties Working Group, most of them volunteers from the astronomical community, who are coming together to help us characterize our stellar population of our targets. We need to know more about the background eclipsing binary distribution in order to be able to assess this statistically for each candidate that we come up with. And we have an eclipsing binaries working group that's working on this, as well as studying the eclipsing binaries in their own science right. Finally, we need to relate the target sample of stars to the general galactic stellar population, because we need to connect the dots. We need to be able to extrapolate from the planets we've discovered around our target sample, which was selected in a very biased way, to the general star that you would find in the galactic neighborhood. So to remind you, we chose stars that we thought it would be really easy to find small planets around. And so there's a lot of bias in the selection there. We need to understand that in order to understand what all of this means. Now, is Occurrence for Kepler? Well, I'd say that probably a couple months ago, I would say there's probably not a good likelihood that we'd be able to continue. In fact, just a couple weeks ago, we concluded tests of the reaction wheels to see if we could get one of the 2 reaction wheels working again. And it was no surprise that we couldn't get them to work. But since the ball engineers were given the direction to see what else we could do with Kepler, rather than trying to do all they could to save Kepler as we knew it, now we know more, and there's more cause for optimism. The ball engineers have determined that there's a way to point the spacecraft and orient it so that it's stable, and you can actually point it using only 2 reaction wheels and use the solar pressure, which is the dominant force that's perturbing the orientation of the spacecraft, as a rudder. And the way you do it is that this is the frame of the spacecraft. The x-axis points out the Boresight, down the Boresight of the telescope. The y-axis points out through the midline of the solar rays. And if you keep the sun on the midline of the solar rays, then the spacecraft is symmetric. and the torque is in a direction that the reaction wheels that we have left are able to counter. So if you can maneuver with your thrusters so that the sun is on the midline, then things are pretty groovy, and it looks like that we can do a pretty good job of maintaining that orientation over several days to a few months. But you have to keep in mind that the Earth is moving in the frame of the telescope. So if you want to point an inertial point on the sky, the sun is moving. So this restricts where you can point if you want to maintain observations over a long period of time. So here's a cartoon. If we orient, so here's the orbit of Kepler in the green, and we're about here in year 4, so we're about half the distance between the sun and the Earth behind the Earth. And if we orient the spacecraft so that the solar rays are towards the sun, but we're pointing along the direction we're coming from, so it's an anti-velocity direction, then we should be able to observe in a cone that's plus or minus 45 degrees from the sun, from this pointing angle. And that allows us to keep the sun on the midline and keep fairly stable pointing for a period of up to 3 months or so. Likewise, we can turn around the other direction and stare at a field that's in the ecliptic for as long as 3 months this way. But if you look in the velocity direction, then the Earth is here too. So I'm not sure what kind of problem that would pose for the kind of science that you might do with it, but it might be preferential to actually look away from the Earth. Anyway, this is all cause for good news. We've released this onto the web so that you can all read about it, but basically how stable you are is determined by the error that you have when you put yourself at this balance point with the thrusters. So these are different curves showing you how the Boresight will roll because of the solar torque exerted on it if you're off a little bit. In fact, the ball engineers think we can do at least this good, and they tend to be very conservative. We've gotten a lot more out of the spacecraft and the instrument than we thought in most regards. So we think this will be typical that over 4 days in one of these attitudes, you can limit the Boresight roll to less than 120 arc seconds. If that's the case, that means that a star in the periphery of the focal plane will only move 3 or 4 pixels. And you can see that if we reset this every 3 days instead of every 4, it's down by a factor of 1/3. So you're only talking about a pixel motion. So this means that there's cause for optimism to repurpose Kepler for another mission for which we can maintain pretty much the same kind of data collection and data processing using existing facilities and capabilities. So we have a call for science cases out now. So people can propose different science objectives to use with a repurposed Kepler mission. At the same time, the NASA Engineering Safety Center is seeking novel hybrid pointing control concepts to see if we can actually do something better than Ball has come up with. The white papers for the science cases are due September 3rd, so in just about a week. There are no constraints on the science people can propose, whether it's near-Earth objects, finding planets using gravitational microlensing. But personally, I think that it's easy to imagine a mission to search for Earth-sized planets orbiting M and K stars in up to 30 fields around the ecliptic, and you could observe each for 2 or 3 months. That would allow you to cover up to 7.5% of the sky, and it would allow you to detect planets in systems that will later be observed by TESS, which is an all-sky transit survey. It will also provide a rich set of planetary objects that you can follow up and characterize with James Webb Space Telescope. Both of these missions are being launched around 2018. But show doesn't stop with Kepler. The show continues. So TESS, which is the Transiting Exoplanet Survey Satellite, was selected by the NASA's Explorer program for launch in 2017, just this year. And its job is to discover Earths and super-Earths orbiting bright nearby stars. That's because TESS is interested in finding the best planets for follow-up and characterization with James Webb Space Telescope, with 30-meter telescopes, with the next generation of missions and instruments. It's going to conduct an all-sky survey. It'll have F, G, and K dwarfs between 4th and 12th magnitude. It'll cover all M stars within 200 light years. And the goal is to observe 500,000 stars over a 2-year period of time to find these planets. So this is what's next. So here's my summary. There's no question that Kepler has been an outstanding success. We've effectively tripled the number of known exoplanets, and I think in another year or two, we can say that we've quadrupled that. I think to really understand our system, to characterize our systems, that we know what it all means it's going to need another 2 to 3 years of data processing and analysis. Multi-planet systems appear to be quite common. They're everywhere. We've had a lot of breakthroughs in asteroseismology, which in its own right Kepler's had an even bigger impact on that field than it has on exoplanets. And everybody's been pushed technologically on all fronts with Kepler. Everybody, even the ground-based observers, have had to update their code to look at our objects. So it's been a lot of fun to see all that happen. So we still have a lot of data to process. We've got 4 years in the can. Only 2 years have been thoroughly analyzed. We're in the final stages now this summer of analyzing the first 3 years of data. So there's no question in my mind that Kepler's legacy will last for decades. Nobody else will collect a data set like this with 4 years of continuous observations on 150,000 stars for a long time to come. And TESS is NASA's next mission to find exoplanets. So I'd like you to join me in raising a cheer for Kepler because it was a fantastic mission, and it looks like the show's not over yet. Thank you very much.